Hi, everyone. Welcome to our monthly meetup. And this meetup, we have a double whammy of machine learning and privacy. With that, we have two sets of research from Fraunhofer. So I'll just start by introducing the first speaker. It's Verena Battis from the Fraunhofer Institute for Secure Information Technology. And she's going to be talking about does machine learning threaten privacy? And a bit of her background, she got a master's degree in statistics at the University of Trier, and she's been working as a research associate at Fraunhofer since March 2019, and her focus is on research into risks to privacy of individuals through the use of modern ML methods, such as neural nets, and the fundamentals that allow for those privacy threats in the first place. And finally, how to mitigate them. So that's what the talk is a lot about too. With that, I will hand it off to you, Verena. So please take it away, and welcome.
Thank you, Trent, for the kind words of introduction. So hello, everybody. My name is Verena Battis. My colleague Lucas Kraner and I, both working for the Fraunhofer Institute for Secure Information Technology. And as Trent already said, today's talk will be about whether or not machine learning techniques threatens privacy. To make sure that we are all on the same page, I would like to start with some definitions. So what's the difference between data privacy and data security, for instance? They both relate to control of the user's data. However, they have distinct meanings. For instance, security means policies and procedures applied to protect sensitive data stored within the company from malicious intruders. These policies help to ensure the core IT security goals, data confidentiality, integrity, and availability. Privacy, on the other hand, or rather data protection, means the protection of persons from the undesired collection, uses, and dissemination of data regarding them. Or probably a more intuitive definition is that privacy is the claim of individuals to determine for themselves when, how, and to what extent information about them is communicated to others. So data protection is a subset of privacy. However, it's not possible to ensure data privacy without a solid security stance. You see, privacy goes even further than the traditional confidentiality term. And why is this necessary? On the one hand, sensitive user data can be exploited by malicious identities to steal or to expose personal information about users, which can lead to financial or social harm, for instance. On the other hand, companies can also use this data to learn sensitive personal identifiable information about users without their consent or without their awareness. Further, we have to define information leakage, which is if a system that is supposed to be closed nevertheless reveals some information to unauthorized persons. Hence, privacy leakage is defined as the disclosure of personal data or information. Equipped with this knowledge, we can directly head to the first example, which is the New York City taxi dataset. Some of you might have heard about this dataset and probably the incident which accompanied the release of this dataset. To give you some details, the dataset contains details about every taxi ride in New York City in 2013, including pickup and drop-off times, as well as their locations, the fare, and the tip which was paid. Each taxi license and medallion number is anonymized in this dataset. So what happened? Some guy realized that those taxi and license numbers are anonymized using an MD5 hash. And for those which are familiar with it, you can't infer from the hash to the raw data. But if you have a clue about how the raw data might look like, you can simply calculate the hash and compare it with those written in the dataset. And exactly that's what happened. The person also realized that there's just not so small number of possible combinations between license and medallion numbers because they follow a specific pattern. And this not so small number amounts to 22 millions. And so the person has a clue about how the raw data look like and what happened. He just calculated all the MD5 hashes for all the possible 22 million combinations and completely de-anonymized the whole data set in this term. Okay. What's the big deal with it? mean, you can use this data set to calculate, for example, any driver's annual income. With only a small amount of auxiliary knowledge using this data set, an attacker could also identify where an individual went, or, for instance, weekly habits. And that's what happened with Riding with the Stars, pretty popular example of this, what happened with this data set. This, for instance, is the route Jessica Alba took one day, and the person just Googled stars getting or celebrities getting out or in a taxi, and you can clearly see the license number and the medallion number. So he could just track Jessica Alba and some others in the city. So, okay, it's not real-time data, and stalking celebrities might be somewhat trivial, but nonetheless, you can reveal information that was not out in the public domain before. And you could, as I said, also identify routines and stalk or even threaten people. Going one step further, let's say you zoom in a specific location. For instance, in this example, a strip club. This map shows the results of the pickups happening outside a specific club during the nighttime, and the yellow points correspond to drop-offs that are closely clustered, which implies, for instance, a frequent customer. You can't see it that clearly in this map, but if you zoom in into the original map, you see the incredible detail of this location data. And, well, for instance, this seems sufficient for blackmailing material, if you ask me. So that's a pretty obvious case of what you can do with background knowledge and additional information. Even though those threats are real and also constitute privacy threats, they aren't the ones I want to talk to you about today. I want to talk to you about machine learning techniques. Such methods, and especially neural networks, are used in almost all areas of life. It's medicine, industry, health, education, entertainment, just to name a few. The problem is that neural networks are mostly black box models. In most cases, we lack comprehensible explanations how the algorithms arrived at their decisions. And in addition, a widespread assumption is that the training is equivalent to anonymizing the data used for training. But recent research has shown that trained networks can remember training data, especially unexpectedly clearly. And this bears, of course, huge risk for the privacy of the individuals. Before we go any further, we have to define the different forms of knowledge an attacker might have. On one side of the spectrum, we have white box. So in a white box setting, you are a firm or a private person or a simple person. You have some confidential private data, which is not allowed to get out of hand. So you keep it in your private environment. And based on this confidential data, you're training a machine learning model. But in contrast to the data, the model is allowed to go public, for instance, via publication. And since the general public is allowed to do whatever they want with the model, they have completely knowledge about the algorithm used, the architecture, the weights, the hyperparameters, you name it. On the other side of the spectrum, we got the black box scene, the black box scenario, I'm sorry. Starts with the same, you're a company, you got some confidential data, you try a machine learning model, but in contrast to the white box scenario, you're not allowed, or you don't want to give the model out to the public. But the public is allowed to query your model via an API. So they just provide input and they receive the respective output, but they don't have any knowledge about the model or its specifications. From a threat model perspective, the assets that are sensitive and are potentially under attack are the training data set and the model itself, the parameters or the hyperparameters, and the architecture. We're going to start with attacks on the training data set, namely model inversion attacks. Just imagine, based on the output of a network, a data point used for training is to be reconstructed, for instance, in image. And just imagine if one could reconstruct a portrait picture, what huge, just to give you a clue about what I want to talk to you. My favorite example for model inversion is Faceception. Faceception is an Israeli company claiming to be able to identify the personality traits of an individual by means of a portrait picture and to assign the individual to an appropriate category. For instance, the categories they use are academic researcher, bingo player, white-collar offender, but they also have categories for like theorist or pedophile. And just imagine you would be able to reconstruct a portrait picture which is used to train one of the last two extremely sensitive categories and the consequences that would come with it. To stick with the face detection example, let's have a look at a face recognition model trained to distinguish persons. Each person in this dataset constitutes one possible output class. And the first or the most one of the most popular model inversion attacks was published by Fredrickson et al. In 2015 and is called pixel optimization attack. So basically, you're starting with a blank input, which could be a black or a white or a gray image, and you optimize individual pixels in this starting image so that the model confidence of the model you are attacking is maximized with respect to the targeted class, for instance, terrorist. Those are reconstructions of this model we are attacked using the pixel optimization attack proposed by Fredrickson et al. You see, these are somewhat recognizable reconstructions, at least if you know the target class, especially for the first and the second class. But the third and the fourth, I would say you can hardly recognize those people if you meet them on the street. However, the model used here is extremely simple. And in fact, it's not even a real neural network, just an input and an output layer connected to each other. So we tried the same technique on a more realistic model architecture, namely a two-layer convolutional network. And those are the reconstructions we got. I'm hardly able to identify a face, let alone a person. Okay, that's not a pretty encouraging result, but that's not enough. We want to have real, recognizable faces. So we came up with the idea to place a generator network in the attack process so that instead of the individual image pixels, the latent vector for the generator is optimized. And here's the result. Sure, it does not resemble the person perfectly, but we have some distinctive features, such as the slightly bigger nose, the bright smile, even the dark hair. And since we use the generator of NVIDIA's style gun, the original reconstruction looks like this. The left one is just a processed image ready to be fed into the target model. But you might notice, if you have a closer look, that we do have some artifacts here in the hairline or in the corners of the image. And overall, the face looks kind of wrong and generated. But to be honest, this was one of the more credible reconstructions. Those are the reconstructions of two other classes in the data set. And those pictures, they not only look a little bit off, they don't look human at all, at least if you ask me. So we went further and basically forced the generator to output realistic face images. And this is what we got. No artifacts, and in fact, it looks like a photograph of a real person, and it retained the prominent features such as dark hair, bright smile, or the visible ears. Still, it doesn't really look like the training sample, but querying the target model with this picture results in a maximum confidence that this is the person depicted in class C1. So this guy over there. And this is the preprocessed image. Okay, we will just have a look at the other reconstructions for class C1. Unfortunately, this does not work out well either. Again, the target model yields a maximum confidence that the person in the image is the guy of class C1. Although we got the gender completely wrong. You might notice that we also have these predominant features of this class in this reconstructed image. Again, the dark hair, the bright smile, slightly bigger nose. So what do we have if not a reconstruction of a training sample? The answer is, here we got an adversarial example. And this is a pretty good example for the importance of explainability of the decision-making process of such models. So far for the special case of face classification model. Remember, in a face classification model, each class is represented by just one person. So there's no big diversity in the training data set for each class. And what if we consider classification tasks with a more diverse database? Those are reconstructions based on the Food 101 dataset. The picture looks a little bit gross, but some of you might realize that this is a representation of the class spaghetti. This is a reconstruction of the ImageNet dataset, and I think it's much better to see that there's an elephant in this picture. And also one based on the ImageNet dataset, this is the class sun classes. And again, this is a pretty good example for a completely different task, namely property inference, which belongs to the reconstruction tags together with the model inversion we just talked about. And the goal of property inference is to extract dataset information which were not explicitly encoded as features or were not correlated to the learning task. And that's what you see in this red cycle. Somehow the model learned the reflection in the sun classes used for training. And that's exactly the point. Property inference aims to extract information that was learned from the model unintentionally. And even in well-generalized models may learn properties that are relevant to the whole input data distribution. And sometimes this is even unavoidable or necessary for the learning process. Moving on to the next asset, which might be under attack, the individual. And what is a membership inference attack? Given a data point, the adversary wants to infer whether this data point was used to train the network or not. Even as less as the information whether a specific data point was used to train the model might leak sensitive information. For instance, the data was used to train a model to detect a specific disease or genetic defect. How does membership inference work? A common approach is based on the confidence of the target model and its decision. Why? Because it's proven that a trained network reacts different to data used for training than to previously unseen test data. If we plot the output probability vectors given by the target network, you might end up with something like this. You see that for data points not used for training, the distribution of output probabilities is somewhat equally distributed. This part in orange, non-members of the training data. But for data points in training, the network is more than 95% secure or certain in most of its decision, here depicted in blue. Given this plot, one could argue that the decision whether a certain data point was included in a training set or not can be based on a threshold. With a well-chosen threshold value, a subdivision could be achieved, but an attacker does not have this information depicted in a graph. So where to draw the line? How do I select an appropriate threshold value? The trick are so-called shadow models. A shadow model is simply an approximation of the target model. And in copying the target model, we copy its decision behavior as well. Based on this information, we can tailor the perfect attack model. So how does it work? Basically, it follows a three-step approach. The attacker has a separate data set, which is called a shadow data set, and it's important to split this data set in half. In the first step, the attacker trains a shadow model on the first half of the shadow data set to approximate the behavior of the target model. Next, he queries the shadow model with the full data set, so with both splits, in order to get the probability vectors of both members and non-members, so data seen during training and not seen. And he assigns a binary label to the probability vector according to its membership status. In the last step, the attack model is trained based on the decision behavior of the shadow model, where the features are the output probability vectors of the shadow model, and the labels are the binary codes indicating whether the data point was used for training or not. This is a visualization why this attack is so effective. The target model is trained on the Cypher 100 dataset, and we are looking at the mean prediction entropy for member and non-member members within each of the 100 classes. So you see the 100 classes on the x-axis and the mean prediction entropy on the y-axis. It is clearly visible that the mean prediction entropy as a measure of dispersion is substantially lower for samples the model had already encountered in training, here in blue, indicating that the model is much more confident about which class the respective data point should be assigned to. We deployed the very attack I just described to you on this target model and yielded an attack accuracy of 95%. So in 95%, the attacker could infer correctly whether this data point was used for training or not. Coming to the last threat I'm going to talk about tonight, which is model extraction. Model extraction has two distinct motivations. On the one hand side, you might be interested in stealing the model itself, which is called a high accuracy extraction. We want the model to perform the designated task as good as possible. This might be the case when the model constitutes a competitive advantage and you do not have the knowledge or the resources to train your own model, and you want to steal it from an opponent or rival. So you would achieve this basically with some reverse engineering approaches. But that is not what we are interested in here. Both attacks I have shown you work best in a white box setting, but usually this is not granted to us. In order to increase the chance of success for the previously described attacks, we have to approximate the target model as good as possible. And that's exactly what we want in a high fidelity attack. We want an as good as possible approximation of the target model to increase the chances of success of the previously named attacks. Meaning that we also want to copy bad behavior where the target model fails to comply with its task. This process, so stealing a model in a high fidelity manner, mostly follows one common approach, which is querying the target model with yet unlabeled data and training the substitute model on the now labeled data points. But where does it work? This process of querying the target model is similar to knowledge distillation, but it's not the same. The common fact, although, is that by querying a model, its knowledge is condensed in its output behavior. And by training a substitute model on this information, it inherits some of the knowledge of the target model. I brought you an example of model extraction, and the orange dotted line marks the target model, which achieved a 75% accuracy on the Cypher-10 test data set. You see one example of an extracted model, a thief model, which is trained on the probability vector without data augmentation and a learning rate of 0.025. And surprisingly, our thief model performed even better on the Cypher-10 test data set than the original models, than the target model. And actually, that's not quite what we are looking for, because we want to copy the behavior. We don't want to improve substantially over the behavior, although it's just 4 percentage points. And we see a second thief model, which is trained solely on the labels outputted by the target model with data augmentation to cope for the lack of information, and also trained with a learning rate of 0.025. And we see that this thief model performs also pretty well. We are just lacking just 3 percentage points below the target model's accuracy. And that's, at least for a model extraction, a complete black box model extraction, where you know nothing about the target model, not about the architecture, about the hyperparameters, nothing's a pretty good example. As I said, our goal is to generate an as good as possible approximation of the target model to increase the chances of success of subsequent attacks. But the question remains, why are these attacks even possible? So early research identified overfitting as a cause for privacy attacks. But Chokri et al. And others clarified shortly after that overfitting is sufficient, but it's not necessary for exposing information from training data. You have to take other factors into account as well. For instance, vulnerable target records or outliers, which might leak information even in well-generalized models, because they have a unique influence in the training instance. Pretty good example for this is a paper published by Carlini et al. In 2019, where they inserted canaries in a language model, a sequence model. And since they inserted an artificial credit card number in a language model, it was the The data point was simply orthogonal to the learning task at hand, and so the model did not have any other chance than to memorize this information. And every time somebody queried the model with the first 2 or 3 digits of the credit card, the model just spilled the whole number. This overfitting, memorization, and retrieval of out-of-distribution data pose a huge potential for both membership inference and model inversion attacks, whereas model extraction is also possible against well-generalized models. Apart from this, other factors have that influence privacy leakage are, for instance, the model capacity or complexity. Even though strongly connected to overfitting, it is worth to put emphasis on this aspect. If the model is too complex for the task at hand, it might start memorizing samples or catch up on spurious correlations. On the other hand, the model type is also very important because certain model types, such as naive Bayes, are less susceptible to membership inference attacks than, for instance, decision trees or neural networks. Different algorithms trained on the same data were shown to exhibit different degrees of leakage. The third point I want to mention is adversarial training. Adversarial training is used to make your model more robust against adversarial example. But it's also shown that adversarial training increases the risk of successful privacy attacks, as already mentioned, membership inference and model inversion attacks. And last, I want to name the dataset structure. The findings here are rather ambitious. Some papers say that the potential of membership leaks increases with the complexity of the data, hence that a higher number of classes led to higher attack accuracy. Some others say that attacks do not scale to complex data sets, and so the attack accuracy decreases. Either way, fact is that the data used does affect attack accuracy and hence the privacy leakage. Your attack works well on the food data set, but does not translate to the breast cancer data set, for instance. So, which brings us to the conclusion of today's talk. So what are the takeaways from today? As I said, many of the attacks work, they are applicable, but they are mostly applicable and only under specific sets of assumption or specific data sets. As I just mentioned, it works well on a food data set, but it does not scale or does not translate to the cancer data set. On the other hand, attacks do not translate well from one learning task to another. For instance, they work in image classification, but they just do not work or work not as good in natural language processing tasks. The current knowledge is mainly based on theory, but we need to know how well those attacks work against systems deployed in the wild. And most of the research on private machine learning is, on the one hand, focused on neural networks, and in doing so, most of them are also focused on small data sets and small models, which might not be representative for realistic scenarios. For instance, neural networks, however popular, are not necessarily the most used models in the real world. But if so, small data sets and simple models might not be realistic either. Okay, for that, on the other side, please keep in mind that there might be interdependencies between research areas. For instance, like I just mentioned, that adversarial training adversely affects privacy. On the other hand, property inference attacks can deduce properties of the training data set that were not specifically encoded or were not necessarily correlated to the learning task. I'm sorry. This can be understood as a form of bias detection. And lastly, we are still lacking a comprehensive theoretical understanding of the reasons for privacy leaks. And of course, this affects our understandings of the limitations of privacy attacks. So that's for my part. Now that I've told you about all the threats lurking in the dark, in the second part of tonight's talk, my colleague Franziska will show you some techniques to protect your machine learning models against those attacks. Thank you really much for your attention. I'm eager to hear your thoughts about this topic.
So thank you very much for the talk. This was very informative, very interesting. So we have right now one question from the audience, and I've got a couple on my own. So for the rest of you listening in the audience, feel free in the YouTube channel to type in some questions, and I'll be happy to ask those too. So the first question from the audience, it's Christopher Moole. He has asked, would it be possible to restrict the confidentiality of a model on training data, maybe by data unlearning?
There are ways of restricting the confidentiality of the target model. You can add noise to it. You can just perturb it. You can give just the top 1 or top 5 probability values. So it is indeed used as a defense. Yeah.
Right, and maybe myself, just to riff on that, the one of them you talked about adding noise, it's sort of the realm of differential privacy. How well does the theory of differential privacy translate to practice? Just to kind of riff on that part.
No, but that's something Francisca want to talk about.
Okay, cool. That's great. No worries. Then we'll defer that for them. Going back to your stuff then. So you had mentioned in the example on model extraction where the thief did better than the original on the CIFAR dataset. What's your sort of hypotheses on why that might be?
Those results I've shown were just some preliminary results, and we're researching right now for another attack strategy. And I think the reason why the thief scored better than the target model itself was because our thief is trained from scratch.
I see. Okay. Also, in the black box model extraction side, you talked about in general extracting models from black box, and it makes me think of how DEC got its start in the early 80s, where they did a reverse engineering of the IBM BIOS, and that was the one thing that IBM kept quiet. But because they did it sort of clean room and reverse engineered it without any knowledge of the implementation, then they were able to have sort of clean IP in order to make their own BIOS, and then they came up with the world's first IBM PC clone successfully, and the law was okay with that. Here, if company X puts out a model and you have unlimited queries of that model for whatever reason, if company Y comes along, or attacker Y comes along, I should just say company, and queries it lots and make their own model, what are the IP ramifications of that? Is it sort of free and clear from an IP perspective in the DEC way, or is there some other set of laws that govern this in some way?
I can tell you if it's fine in a DEC way, but I can tell you that there's a possibility to watermark your model in a kind of way. So if somebody tries to steal your model, you can identify it afterwards. And there are also some other defense strategies, like whether your queries follow a specific pattern, and if the defender realizes that somebody might seems to steal the model, they just perturb the output that they are not useful for the attacker. So they act like normal, but they just give out rubbish.
Okay.
And of course, it's, as you said, it's a violation of intellectual property. So from the side of the law, it should be punishable. You just have to prove that it's your model originally and somebody stole it. And that's something watermarking is pretty good for.
Right. So it's more like it falls under copyright law rather than sort of other stuff. So sort of like remix rights, etc. So somewhere in there. Okay. Thank you. We've got a few more questions from the audience. So I'll just go to the next one. This is from Eric Rodner. Does adversarial training help against some of the attacks, since it would make the network more robust and less dependent on the training examples? And once again, if this is something better to defer for the next talk, just let me know.
So just to recap, adversarial training makes the models more vulnerable against privacy attacks. It makes it more robust against adversarial examples, but it opens other doors for privacy attacks. There are some papers in the last 2 years, I guess, that investigated this connection.
Right. Okay. Cool. So thank you. And I'm just reading the last questions. So there's a paper released early this year. Thieves on Sesame Street discussed some of the similar attack strategies used on BERT-like models. And there are two proposed solutions: membership classification and watermarking. And you mentioned watermarking, and you've been talking about membership classification a lot, but I'm not sure if it's the context meant here. Do you have but maybe to finish this person's question, between membership classification and watermarking as approaches to address this, do you have opinions on which is more effective or practical in production?
Actually, I remember that I read this paper, but I'm no, I can't give you a good answer to this question. I'm pretty sorry about it.
No worries. That's a good scientific answer. Thank you. um, so, I mean, you've discussed some theoretical attacks here. Do you have no examples of attacks in the wild? Like, I could imagine, for example, someone trying to reverse engineer a Google search with, in a black box setting, or even, gray box. That could be worth a lot of money. And, people are probably trying to do that for SEO reasons. Do you know, like, as an example, like, that's a bit of reverse engineering, but I don't know how much it's been approached from a more pure AI modeling perspective. So do you know of examples in general of these attacks in the wild, whether it's reverse engineering models or otherwise?
I know about those attacks, but they are mostly academic research. And they claim that they were able to reverse engineering Google's Vision API
Uh-huh.
for something, I think, a couple of $100, a couple of $100, but nothing in the wild. But I don't think that somebody would tell about it. If
Right.
somebody would steal Google Vision API, they don't want to brag about it.
Exactly right. Or like SEO, right? There probably is some really good reverse engine, like SEO stuff that uses AI, but it's so valuable we'll never hear about it.
Exactly.
Right. And one thing in your discussion and outlook, you had mentioned in the conclusion that right now, there's some pretty big limitations, right, on things right now. The attacks only work under specific conditions. The knowledge is very based on theory, not a lot in the wild. Most research, things don't necessarily transfer. That kind of to me is a sign of research in the early days, which it is, of course. Do you see that, is there any theory saying that it isn't possible to generalize, or to flip it around, are you hopeful that there are ways that these attacks themselves could get much more general and more powerful as time goes on?
Actually, I really think that could be possible. I mean, I hope so. I mean, at least it's the field of my research. It would be pretty not encouraging if I would say, no, that's it. They're not possible to get any better. No, I really think that it should be possible, it can be possible, but we probably don't have the resources right now not the knowledge, not the computational resources to find a way. But and you probably even imagine the model inversion task. So when you want to re-infer a picture, for instance, from the training data. So the early reconstructions were built on extremely simple models, and they were quite blurry and quite noisy. And if you look at the reconstructions built today, I think the name of the paper is The Secret Sharer, published, I think, 2020, so this year. They used a GAN as well, and they had incredible results.
Right. No, that's a great example. And so maybe just to riff on this, and as a final question, so there's basically, theory about attacks, and then some proposed solutions like we'll hear next as well. And then, you're describing how you see that these attacks will get better, and it'll go back and forth and sort of an arms race. Going kind of meta on this, do you see a way to get visibility into this arms race over time? Right now, what I see is, just like, academic papers scattered here and there and so on. But would there be a way to get visibility into what's going on overall? And certainly a lot of it's going to remain hidden because of incentives. But yeah, what would be a way? Yeah, what are your thoughts on that?
I think that's a pretty good question because it's quite hard. I think it's the same problem with security. Everybody wants their programs up and running, and nobody cares about the security, or the security is cared afterwards. The main fact or the main goal is to get the program running and selling, and the same with the privacy part. So they just build something they can deploy to get market shares or to make money, whatever. And afterwards, they realize that there might be some privacy incidents, threats, and afterwards they cannot make up for them. So I think to get visibility for this topic or to get sensibility, you might probably a huge privacy incident that just shows everybody what the repercussions of such a behavior is. Like, for instance, if you're going back to the security incidents with the Marriott Hotel or the Target incidents in, 2011, I guess, something that just shows the people that there is a real threat and they have to make a change.
Right, that makes sense. Cool, thank you. So with that, we will wrap up your talk. So thank you once again, Verena, for the presentation. With that, let's move on to the second speaker. So thanks, Verena. And now we're going to go on to the second talk. The talk is titled Privacy Preserving ML. And the speaker is Franziska Bonisch. She's also with Fraunhofer Institute for Applied and Integrated Security. And a bit of her bio. She has completed a master's degree in CS at Free University Berlin and TU Eindhoven. For the last year and a half, she's been working at Fraunhofer as a research associate in topics related to privacy preserving ML, data protection, and IP protection for neural networks. And she's currently doing her PhD in Berlin. Please take it away, Franziska.
Yeah, thank you very much for the introduction. I'm glad to be speaking at this event tonight. And yeah, like Trent already presented, I am working at the Fraunhofer Institute for Applied and Integrated Security. And most of my projects at work and in my PhD are centered around privacy preserving machine learning. Therefore, I'm really excited to be talking about this topic today. And I put my LinkedIn account on the slide because, like, in this remote setting, it's quite difficult to get in touch afterwards. So if you want to drop me a message, if you find the topic interesting, just write me a message and we'll get in touch. Concerning the talk tonight, I think that I'm in a really lucky position because usually you start your talk with a motivation and you make up an example that motivates that all you're doing is really necessary. But I think now, with the great talk given by Verena, it's already quite clear for everyone that there are so many threats against your machine learning models out there. So you need some protection. And fortunately, and this is what my talk tonight is going to be about, there are some techniques to protect the privacy of your machine learning models. Some are rather new methods, some already existed in other fields and were just adapted to fit machine learning. Given the time here in the talk, unfortunately, it's impossible to present all the methods in depth, so I chose for presenting the method that I'm mainly using in my research, namely differential privacy. However, I still want to give you a little impression on the other methods that are out there so that you can identify the threat scenarios and see what methods might be suited for what scenario. So we will start on having a look at the methods and seeing when to apply them, how to apply them. Then we will jump a bit deeper into differential privacy. Afterwards, we'll have a look at how to apply this concept of differential privacy for machine learning. And at the end, I will show you some practical evaluation that I've done through my work and give you some takeaways on the topic. So let's get started on the overview. Usually, when you want to add privacy to your machine learning model training, you will have to focus on a specific method. And usually it's quite difficult to decide which one you want to use if you're new to the field. And basically, I would say that there are some main questions that one would need to answer before deciding on the method. The first question concerns the parties involved. So in the training of your machine learning models, is it only your company that is involved, or is it maybe your whole team, or just some people of the team? is maybe some data coming from another organization, and can this data be shifted to you, or is every party keeping their shares of the data and you need to kind of have the training somewhere in between them? The next central question is the question about where do you want to train your machine learning models? So are we in a centralized system where you first collect all your data from your data sources and then you train the model centrally? And then the question is further, what is your infrastructure about? Is it your own infrastructure? Do you protect it? Can you trust in it? Or do you need to rent out some other GPU power, for example, by Amazon Web Services? And what about the ways of transit to the server and the way back? And do you trust in the data to be kept secret on that server? And then the next question is also, would you maybe like to deploy your model directly on the client's devices? And then there's another question, is it low-level devices like IoT or smartphones? Or are you directly offering a server with a prediction API? Afterwards, the question that needs to be answered is the question about who is training the machine learning model. So if there are several parties involved, it might be very clear from the beginning that not everyone is allowed to see and access the data, for example, by some legal restrictions. But even if it's your data, there might be some restrictions that not every developer might be allowed to see all the data points. So you would need some access control such that not everyone can see the data. And the last question that you should ask yourself is about the computation capacity. So it's clear that if you add another security goal to your machine learning model training, namely privacy, this will add a slight overhead to your workflow. So you might either need more storage, for example, to store the original and some perturbed data, or otherwise you might need higher computation power if you perform more complex operations. Or otherwise you might, for example, need a higher bandwidth for communications in between parties. So this is basically everything that you need to know beforehand if you can afford these additional costs and which one are more suited for you. And based on that, you can choose for your method. The methods that we are going to have a look into tonight are homomorphic encryption, secure multi-party computation, federated learning, and then at the end, we will jump into the topic of differential privacy really deeply. The setting of homomorphic encryption is a setting where you have some private data, like in this example, some medical data, which shouldn't be seen by someone else than just your organization. And probably you don't have the resources to train your model locally, so you rent out a server with high GPU power and you want to train your model. However, all on the way to the server, on the server itself, and on the way back for the result, your data is unprotected. So someone else could see it, steal it, or just like make any privacy loss to your data. Therefore, homomorphic encryption proposes taking the data locally and encrypting it. Then you send the encrypted data to your server and use homomorphic operations. Like a homomorphic operation is one operation that takes encrypted data, produces a result, and if you decrypt the result, you have the same result as if you had performed the methods on your clean data, on your non-encrypted data. And by this, you achieve encrypted data to pass over the transit. You have your private data on the server, and also the results are encrypted as long as they're on transit, and then you can decrypt them and have your results. So this is basically fine, but still all those homomorphic encryption operations need high computational power, so they might not be suited for every scenario. Another scenario is the scenario of federated learning. Imagine you're in a distributed setting, for example, where you want to learn something on your customer smartphones. And of course, what you could do is to collect all the training data from your customers and then train your model centrally. But you don't have to do that. And especially sending all the data around all the time has high communication costs. And this might be unnecessary for your customers who also maybe have a limited amount of internet on their phones. So you want to avoid this. And instead, what you do is you start to train your model locally, and then you distribute the model to all your clients and have them improve the model with their local data. So what they do is they don't send their new data anymore, but they train the models locally and produce some updates to the model. Afterwards, those updates are recollected and sent to the central server again. And there you can combine them and basically make a update step to your entire model. However, as we know, weight updates to machine learning models can also be privacy disclosing, for example, if they point to a specific direction. So what you should also add is some noise on the weight updates. And afterwards, you need to average out this noise over all the updates you got. And of course, this requires a lot of data. In federated learning, there is a special security risk, namely the fact that you can't really see what data your clients are training on. So you could imagine that there are malicious parties who just perform some malicious updates and send them to you, and you don't really have many ways to verify how they are, like if they are benign or if they are malicious, and you just need to figure out something there. The third method is secure multi-party computation. And secure multi-party computation is actually a subfield of cryptography that has the goal to create methods for parties to jointly compute a function over their inputs while keeping those inputs private. For example, here, these institutions could be hospitals that have patient data which they are not allowed to share with each other because of the GDPR or other legal restrictions. And what they then do is to share secret parts of the data with each other that only all together can be identified as the data. So as long as these shares are only distributed, they are private, and then all those parties together approximate a function, which can be anything simple from an addition up to a complex function like a neural network. And secure multi-party computation is closely related to homomorphic encryption from the principle, like you compute a function on a private input without revealing anything except the final output. However, in difference to homomorphic encryption, here you use not really extensive operations, but a lot of communication overhead. In differential privacy, we are in a slightly different setting. The setting where we have actually all our data with us and we want to train the model like in the usual machine learning workflow. The threat doesn't come from a server that we mistrust or so, but we are afraid that analysis we conduct on the data could disclose some privacy of the training data itself, or that a deployed machine learning model could leak private information. And this might be hard to figure out. Like for the machine learning models, I think you got a good idea in Verena's talk how this could look like. But in usual analysis, it's maybe not so intuitive. Therefore, let me give you a little example how analysis on data could be privacy disclosing. Imagine you have a group of people and you want to compute something about them, for example, their average height. So you take the data points and you compute the average. So far, so good. It doesn't look so privacy disclosing yet. But then imagine there is this orange person joining the group of people. And as you can already see, this orange person is much taller than the green ones. So its data point may look like this. And if you compute the mean value, you end up with a much higher mean than without this person. So even for an outside observer who just sees both mean values, it becomes clear directly that the person in which the data sets differ is much taller than the other ones, and so privacy of this person is disclosed. What you can do to protect the privacy of the person is to put some noise on the data. Usually the noise that you use, therefore, is Gaussian noise or noise from a Laplace distribution. Like I put the distributions on the slide again just to remind you how those would look like. And then you put this noise on the data points. They might change slightly to look a bit like this. And the new mean values look like 1.74 m to 1.75 m. So they don't differ so much anymore. And therefore privacy is preserved. As an alternative to putting noise on the data, you could also put some noise on the algorithm. Imagine you have this normal computation and then you just compute your normal mean. But then before outputting the result, you add another step to your algorithm, which is adding noise. And then you could end up with values that look like this. So also this way, the privacy of this orange person would be preserved. And this is basically also the idea of differential privacy. the questions that come up pretty quickly after seeing such an example are, first of all, how much noise do we need to put there? Because given the green people and the orange people, you know how much they differ in height, so you can adapt the noise level to hide the height of this orange person. But as you don't know your data before, you don't know how tall the green people will be, how high the orange person will be. So actually beforehand, you cannot know how much noise you will need. The next question that comes up is, whose privacy do we want to protect? Now we spoke about protecting the privacy of this orange individual, but consider that it might be possible that another individual, like a pink individual, joins the group who is even taller than the orange one. So the noise wouldn't be sufficient to protect it. And the last, and in my opinion, most interesting question is the question, how much privacy do we want to grant? So we saw that the results together, it could be close as 1.74 m to 1.75 m, so 1 centimeter in difference. Is that okay? Is that enough as privacy, or do we even need a smaller difference? Or could we even live with a difference of 2, 3, maybe 4 centimeters? Luckily, differential privacy has an answer to those questions. And before we will look into the formula, let me give you a little intuition behind the concept. So differential privacy informally states that in order to protect privacy of an individual, the results of performing an analysis on any dataset D1 without that individual should be roughly the same as on the dataset D2 with that individual contained, but otherwise like similarly as D1. So if we take that over any data set, that means we don't know beforehand how tall the people will be. And if that holds for every individual in the data set, then we have privacy. The amount of privacy thereby is defined by this notion of roughly the same. I think that now we are ready to look into the formula. The formula states that if we have a randomized algorithm M, in our case, this would be the noisy average function. This algorithm gives us epsilon differential privacy if for all neighboring data sets D1 and D2. So D1 is the data set with the green people only, and D2 is the data set with the green people and the orange person together. And then we have an element S that lies in the image of M, so it's one of the results that M can produce. Then the differential privacy definition states the probability that when we execute M over the dataset D1, producing S should be lower equal than e to the power of epsilon times the probability of having the same element S when we execute the algorithm on the dataset D2. And you can see here now that this definition, roughly the same, is expressed by the value e to the power of epsilon. And there, like epsilon basically defines how much privacy we can provide, and therefore it's also often called the privacy parameter or the privacy budget, as it defines how close the results have to be one to another. Therefore, it sets a mathematical upper bound to the privacy loss. As you can see by the equation, it follows that if we have small epsilon, the two results will not differ a lot. This means that we have really high privacy. If we have rather large values of epsilon, they will differ a lot, so that we have lower privacy. Unfortunately, in literature, there's no definition on what epsilon must be like. So many people consider this as the largest drawback of differential privacy, because if you set this parameter of epsilon incorrectly, then you allow for a too big derivation. And you still say, well, my data analysis is differential private, and that sounds really fancy because there's a word private in it, but actually you don't achieve any privacy, and you just have people with the wrong sense for security. Research, however, suggests that you should take epsilon values in the range of 0.1 to 1, and other values that are higher should be used very carefully. What one can do in order to see whether the protection value offered by epsilon is good enough is to run some of the attacks described by Verena and see how and to what degree they are successful. And if they're not successful anymore, you see that probably your privacy level is enough for the moment. Additionally to the normal definition of epsilon differential privacy, there's a relaxation, which is called epsilon delta differential privacy. And this is a definition where we just add a little term here, the delta term. And delta defines basically to what percentage of the cases the strict bound of privacy loss is allowed to fail. Usually, therefore, delta should be set to something smaller than 1 divided by the number of data samples. Now that we know the differential private formula, it's quite like it's not 100% intuitive how we can apply that for machine learning, because there are also some questions remaining. And the most important one is, where do we add the noise? The first option that was considered was actually adding the noise to the training data. But usually this is not a great idea because your model is trained to recognize some correlations. However, if you put some individual noise on each attribute, you risk to destroy the correlations and thereby render your model useless. Also, in machine learning, you might have features with different ranges. You might have numeric features, categorical features, and all of them usually require different amounts of noises. And of course, to have a unified level of privacy, you would always need to take the lowest value of epsilon, so the highest privacy. And thereby you might add so much noise that the model is not useful anymore. Another option is to add the noise to the prediction output, and this is possible. However, it's quite hard to analyze how much one model can be changed by an individual data point, because we've seen the level of noise basically depended in our example by how much the orange person could change the derivation of the mean height. So in machine learning, it's really difficult to predict how much one data point will change the model output, and therefore it's really hard to set the right amount of noise. And you would potentially add too much noise, and the model might not be useful anymore. Therefore, the best option that is known so far is adding noise during the training procedures. And this has another advantage. You end up with a model that is actually private. So also there are no side channel attacks possible to your models. Other than if you put it to the prediction output, then your model is still non-private and someone can attack the model in a different way than over your API probably. And I would like to present to you now the two methods that are used nowadays in order to achieve differential private machine learning. And the first algorithm is the so-called differential private stochastic gradient descent. On this slide, so far, you only see the normal stochastic gradient descent that should be familiar for everyone. You have your training examples, x1 to xn. You have a loss function defined. You set the parameters, the learning rate, and the group size, which can also be called batch size. You initialize your model weight, and for every epoch, you sample your batches, you compute the gradients, and then in the descent step, you move towards the negative direction of the gradient with your learning rate, and at the end, you end up with your trained model. The differential private stochastic gradient descent algorithm is actually not so different from that. You just need two more parameters, the first one being a so-called noise scale, and the second one being called the gradient norm bound. Sometimes it's also called the L2 clip norm, and I think this is easier to get because it represents more what this capital C is actually doing. So from mainly all steps, the differential private SGD looks the same as the normal one. However, after taking the gradients and calculating them, you add some more steps. The first step is that you actually clip this gradient. You allow all gradients to be at the value of maximum capital C. And this offers you the advantage that no more data point can have a really, really large impact on the model, but the impact of every data point is limited. So you avoid that a model basically focuses too much on a data point, or a data point contributes way too much on your learning process. And then what you do is you add some noise from a Gaussian normal distribution, and thereby you dissimulate the points even more. And then you perform the normal descent step, and you can output the weights like a normal model. And then you can use some functions, some privacy accounting methods to compute the values of epsilon and delta from your noise scale, your L2 clip norm, your learning rate, and the number of examples. Another possibility that can be used to perform differential private model learning is the so-called Battis algorithm. And this basically has another approach where it's not about altering an existing algorithm and then providing the model that has already seen the training data. But here it's about another idea, another principle. And what you start off with is taking your data and cutting it into different chunks. All of these chunks need to be disjoint, so there are no data points that are present in more than one chunk at the same time. And you take those training data points and you use them to train a model individually. The Battis algorithm doesn't specify what kind of models you need to use here, so they do not even need to be the same kind of model. It can be one logistic regression, one neural network, and whatever you like. And then you have trained those models, so they already have an understanding of your task. But of course, there are privacy risks in those models because they might have overfitted some data, they might be very close to some data, they might memorize it, and attacks would be possible. So therefore, what you do is that you take some additional auxiliary unlabeled data. This can be some, for example, some data that you find in a public data set and it looks quite similar to the data that you have for your task. And what you then do is you take this data and you make the teacher that we have label it. So the teachers, they predict on this data. And then what you do is you take all those predictions together. And here at this point of aggregating these predictions, you add the noise for differential privacy. You end up with a noisy aggregate that corresponds to a label for the data. And what you then have is some unlabeled data, some labeled data. And of course, what you can do with labeled data is to train another model yet. And this model is called a student model because by this transmission process, it kind of learned what the teachers learned on your private data. But it has the great advantage that the student model has never seen your private data. So there is no way one could restore your data from that model. If you want to be very safe, then you take your teacher models and you enclose them in a safe or you just delete them. You end up with the student model and you use that for deployment all the time. I think this is a pretty awesome approach. Now, let's see how this works in practice, actually, both of these mechanisms. When I started using differential privacy for machine learning 2 or 3 years ago, honestly, it was a niche in machine learning, but nowadays there are so great libraries that support you in your development. For example, I use the TensorFlow privacy library, and it's pretty easy to use the differential private methods that I've just shown, like the DPSGD or the Battis algorithm. And the TensorFlow privacy even offers some implementations of the attacks that Verena has demonstrated. For example, you can easily perform membership inference attacks. So it's a one afternoon activity to look at how vulnerable your model is to membership inference attack with differential privacy and without differential privacy. And you will see basically that differential privacy can indeed mitigate those attacks. However, there are some little things to take into account. Like when I first started using those libraries, I thought let's use them on a basic task, for example, MNIST, because MNIST is really easy to learn. And I created a baseline model, which is not surprising. Without any fine tuning, I achieved really good results with a really small ConvNet. And then I thought, well, okay, I'll just do the same for a differential private model. I set the parameter values to have a good level of noise. I started the training process. And what you need to know is that differential private training takes much longer than normal training because instead of doing all those updates for the entire batches, you need to iterate over every training data point, clip it, put noise on it, and then do the step. So therefore, I saw that the accuracy was rising at the beginning. I went off to have a coffee, work on other things. And when I came back an hour later, I saw this result. And I thought, well, maybe differential privacy is just not suited for the task. Maybe my privacy value of epsilon was set too low. But then I invested some time into the hyperparameter tuning. And after a short while, I ended up with a model that achieved the same level of privacy, however, with this classification result. And I found that the difference was just in how I set the parameters. I set the same level of noise, but I set different clipping norms. So here you see that it's very, very important to fine-tune your models. And the problem is still that if it takes an hour already to train a really small MNIST model, it takes a day to train a cipher differential private model. And this makes hyperparameter tuning at the moment still very inconvenient, in my opinion. However, of course, you get a feeling for the parameters and then don't end up with such horrible results at the first place and can maybe narrow down your search space directly. So all in all, I think the takeaways that I can give you is that there already exists really convenient libraries to train your model with privacy. For those who like TensorFlow, you can use the TensorFlow privacy library. For those who prefer PyTorch, you can use the PySIFT library. It has exactly the same functionalities. The pre-training is, of course, much more computationally expensive than normal model training. The TensorFlow privacy library offers you a possibility to kind of decrease the cost of training for the models. They introduce a new parameter, which is the mini batch size. So instead of doing the clipping and noise addition for every data point individually, what they do is to have those mini batches that divide every batch again into smaller batches. And then you take the average of all points in those batches, clip them, and then add some noise on them. The problem with that is that you are always a bit in this trade-off between privacy versus utility versus computation time. So if you want very high privacy, your utility might drop a bit. You saw that my MNIST model, even with a fine-tuning, only achieved 90%, whereas the baseline model was already at 97% validation accuracy. And then you have, of course, this computation time issue. So if you use those mini batches, be prepared that you will also lose some of your utility. So this is a basic, a narrow road to fine-tuning those models. And of course, all those hyperparameters need to be tuned very carefully. For example, in the differential private stochastic gradient descent, we have the noise scale, the clipping norm, and the mini batch size. But in the Pate algorithm, it doesn't look so much better, because we have the number of teachers that we can set independently. We have the types of the teacher models, and if we want, we can fine-tune every teacher model by itself again. So it looks like a big amount of work, but still, I would say that it's worth it for having models that include your privacy. And that being said, I would like to thank you for your attention, and yeah, go on to the question part.
All right. Thank you very much for the talk. Really, really useful and informative, and a cool follow-on to the first part. So, although you did point out some more problems too, we wanted only solutions. No, all good. So, yeah, for the audience, please, if you guys have any questions, please feel free to post them, and I'll just start with some questions here of my own. I'll start from the beginning of your talk. You had mentioned when you were surveying federated learning that there was the question of the local trainers, giving their weight update. And there was a few techniques that had been proposed to know if a local trainer was trustworthy. Could you just quickly survey and just give us a brief overview of what those techniques are and what might be good or bad?
Excellent. Could you repeat the question, please? What techniques?
Sure. So yeah, so in federated learning, you had said there's this challenge of how do you know if one of the local nodes that's doing a weight update is trustworthy or not? And then you had said that there were some ideas on how to do this, but they each have their pros and cons, their advantages and disadvantages. Could you elaborate on what some of these techniques might be on addressing?
Of course. Well, I'm not the expert on federated learning, but I know that there are some methods where you compare your model updates, for example, in groups. You look at how do the updates by all the people look independently, and then you look out for updates that are too close to each other, so that point too much to the same direction, because this could be a threat of some people putting malicious updates to jointly force you to a specific update, and then you would just block those groups or like limit their impact. This is one method that you could use. Other methods would be to to just perform those updates and see where your model is going on a validation data set that you have prepared and that is kept secret. So you can still observe how your model is developing over those updates.
Right. Okay, thank you. Cool. Next question. So from what I gather, in differential privacy, the epsilon, it's not treating, it's basically approaching it from a sort of L2 approach, right? So it's sort of a ball as opposed to one L1, you know. So that means that if it is like that, then it's going to be very dependent on dimensionality. Could you give a feel for how dependent it is on dimensionality, how well it can scale to more and more dimensions? Maybe it's not. Maybe, yeah. Maybe, yeah.
So yeah, you're right. Definitely, with this observation, differential privacy comes from the domain of aggregate queries. So the query that it was designed for and that it worked best on was the counting query, because every counting query, if you have a data set with a certain data point or without a certain data point, the difference of the results would only be at most one. And so it was very easy to dissimulate these differences with epsilon. So this is why also those classic approaches of using this epsilon on some, just to perturb, for example, some output, they would be very vulnerable to dimensions. And this is why we don't use this epsilon in the classic way for machine learning training. Machine learning differential privacy training looks a bit different under the hood, to be honest. Like, this version is a much simpler, it's like the version how I presented it is a bit simplified. In general, what it's based on is that you don't really take this epsilon into account during your model updates, but you just have these clipping norms and you have the noise scale. And from those values, you at the end calculate an epsilon, but the epsilon is not really it's not influencing the training process.
Oh, I see. Okay. Okay, I see. Thank you. The next thing, and for the audience out there too, please feel free to post questions and whatnot. I'll have a couple more here. Maybe just a simpler, higher level one. I've seen, for example, Apple make claims about using differential privacy on the iPhone and whatnot. So overall, what is the usage of differential privacy in industry, or is there usage, or is it just marketing?
Yeah, I think you named one of the most prominent examples, Apple. Apple uses differential privacy even in the core product. So they use it for word suggestion, so to learn custom dictionaries. They even use it for the health data. However, in their first implementation, they directly did not do it entirely correct. There was a paper afterwards, really shortly after they launched their differential privacy, that discovered that they were using it in such a way that the privacy loss was not limited to epsilon, but on the entire lifespan of the data, but that you would use up this privacy budget each day anew. So at the end, they ended up having an unlimited budget. But I think that they fixed that afterwards. Another really prominent example for using differential privacy is Google. Google uses this differential privacy in their Chrome browser to do some statistics. For example, how many people are using what kind of start page, what autoplay is usually dismissed, what autoplay can go through. And therefore, they have some differential privacy techniques deployed. Another example who uses differential privacy and also has a large differential privacy library online, which is now, I think, not maintained anymore, but it's Uber. So you have really big examples in the industry. Also in Germany, who is pretty big is SAP, but they don't use it on machine learning, but only for normal queries, so far as I know.
Okay, cool. Thank you very much for that. And maybe one more question for myself, and then when you talked about these two algorithms for differential privacy, the second one, DP Pate, is it pronounced, or Pate?
Mm-hmm.
Probably Pate, right?
Yeah, like the French liver pate.
Makes sense. The North American in me would just say Pate, but anyway, makes sense. So, at a first glance, it looks like it takes some of the philosophy of synthetic data generation, right? Where you just have some compute to data at the level of the next to the data, where it computes something synthetic, and then from that you learn a model from the synthetic data, right? But in this case, it sort of tries to have a few more levels of misdirection, where instead of just having a separate data set, you've got a model, and then you have many models aggregating. So maybe could you, I don't know if you are deeply familiar with synthetic data, but if you have some experience or some thoughts, could you elaborate a bit more, maybe the difference and the strengths and weaknesses of DP Pate versus synthetic data, please?
Sure. Like I think for me, what Pate basically looked like when I had the first look on it was ensemble training. So this is even more what I had on mind when seeing this algorithm instead of synthetic data. But actually, the original Pate paper also introduces ways how to generate synthetic data with this algorithm, with this exact one. And this is basically, then you have the teacher models, and they are used to train a discriminator. I'm not exactly familiar with the details, and then you can generate synthetic data with that. This is all done in the Pate paper.
Okay, cool. Thanks for sharing that. And looks like now we have a couple questions from the audience. So from Louis Herman, he has asked, can you explain again why the gradient descent, so I guess this is DP, stochastic gradient descent, why that should be done sample by sample as opposed to batchwise?
Of course, because this is a question for the utility in this point. You want to go over each data point individually in order to preserve what they contribute to the gradient. So if you take all the gradients and average and then just clip, you might lose some information. This is why you go over a sample per sample base and not over the entire batch.
Okay, I'll follow up. There's another question from Louis Herman. The clipping norm is fixed, the noise is fixed, and the expectation values of the gradient update changes only slightly when batching. Why not clip and noise all gradients from the batch?
I think it's because usually, like, if you should set the clip size such that not every gradient is clipped to the same value. So you set the clip size such that it's larger than many of your gradients. So most of the gradients will not even be clipped. And yeah, I think.
So the clipping setting is sort of like a percentile function, right? You want to clip at the 80 percentile level, rather than just some arbitrary number that could be 80 percentile or could be 10 percentile depending on the data. That's
Exactly.
the general, right? Okay. All right. That's all the questions from the audience and from myself. Did you have any final thoughts or comments from the questions, I guess I should ask then? No, okay, that's good. So overall then, I guess that takes us to the end of our two talks for today. So I want to, just extend a hearty thank you to you, Franziska, for your talk, and back to Verena to you, Verena, for your talk. Thank you very much. We really appreciate it. And and also on behalf of the audience, thank you very much. With that, I'll just give a couple more notes on what the meetup is too. So we meet up typically the first Monday of every month, and always, these days online, of course. Hopefully that will change at some point, but still online. If any of you in the audience are interested in giving a talk, please just reach out to us on Meetup or otherwise. Myself, I'm Trent, and my organizer is Abhishek, and I have two other organizers that couldn't make it tonight, and that's Daniel and Adrian. So reach out to any of us. And also, I do want to give a thank you to Abhishek for managing all the IT and stuff tonight. So yeah, with that, maybe I'll just ask Abhishek, anything from your side? Did you want to say a thank you too?
Thanks a lot to both the speakers, and it was a very good talk, and hope to have the meetup in Berlin someday soon.
For sure.
Thank
Or
you very
maybe
much.
we'll do it in Norway if it's less locked down.
Yeah.
Of the Norway edition.
True.
All right. Well, exactly. So with that, thanks everyone, and have a great evening. Take care. Bye.
Okay, we are out.